Good morning. I'm Fulgencio, and I'm a student of Professor Donato and Professor Gibe from the University of Rouen in France, but I'm also affiliated with the Institute of Mathematics in the University of the Philippines, Diliman. Before I start my presentation, as everyone did, I would like to thank the organizers for inviting me and accepting me in this wonderful discussion meeting. And I would also like to thank the participants for a wonderful interactions and conversations. Okay, so I will present our existence results on quasilinear elliptic problems in a domain with imperfect interface and L1 data. So for my outline, it's just a simple outline, statement of the problem, and then I will talk about some related works, and finally, I will present our results. So our problem is on a fixed domain. We consider the following elliptic problem on a fixed domain. So here, we have the usual heat propagation on the omega. I will talk about omega 1 and omega 2 later, but we already saw that. We have the Dirichlet boundary condition, U1 equals 0, and on the interface, we have the continuity of the flux, and the jump of the solution is proportional to the flux. Okay, so our domain, omega, so I think we've seen this enough. Basically, you can just write omega as a disjoint union of omega 1, omega 2, and gamma, where gamma is the interface. And if you have a function defined on omega minus gamma, then the restriction of u on omega I is ui. Okay, so our assumptions. The difference with the previous presentations is just f, our data f, is an L1 function. The rest is just standard, so h is L infinity with the lower bound, and b is a caretidori function with the ellipticity condition. And we have this sort of different, but it's almost the same, condition on b, which is b is L infinity on omega cross negative k to k. This is an interval for any k. Okay, so the space that we will be working with is the space V. Again, this is already defined. So V1 is the set of all H1 omega 1 functions with 0 value on the boundary. And we endow this with a norm, L2 norm of the gradient. While our space V are all the functions such that the restriction on omega 1 is in V1, while the restriction on omega 2 is H1 of omega 2, and again, we have this norm. So for some positive constant, sigma. And this given norm is proven by Monsuro that this norm is equivalent to the norm of V1 cross H1 of omega 2. This is important because we want to use the compactness results in L2, so we want this equivalence. Okay, so how is this related to homogenization? So I just want to mention that our main goal is to homogenize this problem in a two-component domain with imperfect interface. Yeah, we've seen this again. The domain is like the one presented by Ivy, Elia, and Elia. So a two-component domain. Okay, so just to mention some work, before I forget, this presentation is just the existence result for this kind of problem, so it will be a short presentation. Okay, so existence result. So some works related to this problem. So on the variational case, on a fixed domain, this was done by the MS thesis of Beltran. So that is F is in L2. While the homogenization on a two-component domain using the periodic unfolding method It was presented by, first, Donato, Lenguen, and Tardu with linear heat flux, that is, the flux is proportional to the jump. While in the second one, Donato, Lenguen, they presented the flux is a function of the jump instead of being proportional. For the quasi-linear case, linear case is the matrix field A is independent of the solution, while the quasi-linear case, that is, the matrix field is dependent on the solution. It is presented first by Beltran in his MS thesis, the one I mentioned, and it was continued by Borja the next year, continued and finished the homogenization process with corrector results. Okay, so for L1 data, since we don't have the Lax-Milgram theorem, so we have to introduce a notion of a solution. Since weak solutions, we cannot use the weak solution framework. So we have what we call the renormalized solution. And this framework was introduced by Di Perna and Jung in 1989 for first-order Boltzmann equations. And it was developed for elliptic partial differential equations by Mura in 93 to 94 for L1 data, and Dalmaso and et al. For bounded radon measure. And this framework gives us existence, stability, and uniqueness. But for uniqueness, we have to give more conditions on the operator. And for the combination of renormalized solution and periodic unfolding method on homogenization, I only know of one paper that did that, which was Donato, Gibe, and Oropeza in 2017. And this was done in a perforated domain, the one with holes. Okay, so now just some results. First, I would like to define the truncation function Tk at height plus or minus k. Yes, we've seen this before. So this is the graph. So Tk of t is t for t between negative k and k. T less than or negative k for t less than or equal to negative k, and k for t greater than or equal to k. So this truncation function is important for the renormalized solution framework because since f is in L1, our solution may not be in a Sobolev space or in an LP space. So using Tk, we can define the gradient and the trace of our solution U. So for the definition of the gradient and trace, we have the following proposition. If we have a measurable function where the truncation is in V, then by Benilan et al., we can find a unique Vi such that the gradient of Tk of Ui is equal to Vi times the characteristic function of this set. Absolute value of Ui is less than K. And this unique function Vi will be our gradient of Ui. And for the trace, we have an additional condition that the supremum of 1 over k times the square of Tk, the square of the norm of Tk of U in V, this is finite. Then we can find Wi such that the trace of Tk of Ui is equal to the truncation of Wi. And this unique Wi is will be the trace of Ui. So I forgot to write here, but for I equal to 1, this was proven by Gibe and Oropeza in their paper before the homogenization. And the proof for I equals 2 is almost similar. I think the main difficulty is we don't have the Poincare inequality for omega 2 since we don't have 0 value on the interface. But otherwise, it's almost the same. Okay, so since we now have the gradient of U and the trace of U, we can now define the renormalized solution of our problem P. So for our problem P, U is a renormalized solution if the first two conditions are regularity conditions. So we have the truncation of U is in V for any K, and we have this U1 minus U2 times Tk of U1 minus Tk of U2, it's in L1 of gamma. While the other two conditions are decays. So this is, we don't know how to call this, so we just call it decay of the truncated energy. And this is the decay on the boundary, on the interface. And of course, we have the renormalized formulation for a C1 function with compact support. Then you must satisfy this formulation where our test functions must be functions in V that are bounded. Okay, so the main question that we have is, do these integrals make sense? So that's the first question. So for the conditions, the 2a, Tk of U in V, and this decay of truncated function, truncated energy, this is standard in the renormalized formulation. So if Tk of U is in V, note that since S has a compact support, then this omega I, so we can write this integral as just the integral on the set where Ui is bounded by some constant. So by definition, this Ui, gradient of Ui, will just be the gradient of the truncated of Ui. So this is in V, this is in V, this is L infinity, and this is also bounded, so it's L infinity. So this makes sense. Similarly, the other three integrals make sense, the next three integrals. So the main difficulty that we encountered here is making sense of this one, the integral on the interface. So usually, for renormalized framework, we don't have the jump of the solution on the interface. So we don't have the integral on the interface. So now that we have the jump, we have to make sense of this integral. And this was achieved by adding this regularity condition, that U1 minus U2 times Tk of U1, Tk of U2 is in L1 of gamma. Okay, so these two conditions, the first two, gives sense to the integrals here. This is also makes sense because Vs of U is bounded. So F is in L1, so we have that. So this two makes sense of the integral, while the other two, these are important for our uniqueness results, which is in progress in work, and also for recovering that Tk of U, the truncation of the solution, is an admissible function for our problem P. Okay, and that is important for stability results. Okay, so this is what I just mentioned. So now we go to our main result. I told you this is a short presentation. So for our main result, we have that there exists a solution. There exists a solution to P with assumptions A1 to A3, the one I mentioned before. So I will just give the idea of the proof. So the proof is divided into 4 steps. So the first step is by solving an approximate problem. So for the approximate problem, we approximate first F. We approximate F in a sequence in L2, and we define B epsilon of xt as B of x t 1 over epsilon of t, and we have this approximate problem. So we just replaced F by F epsilon and B by B epsilon. And this one has the variational formulation of this one. And the proof of existence of solution of this problem is quite standard via Schroeder's fixed point theorem, which was explained by Federica earlier. So we found a solution to this approximate problem. So the next step is to extract subsequences. I'm almost done. Extracting subsequences and examining some convergences. So if U epsilon is a solution of the approximate problem, then we can show that Tk of U epsilon is a bounded sequence on in V. And by extracting some subsequence, we can have these 5 convergences. And Ui or U equal to U1, U2 will be our candidate for a renormalized solution. So from the first 4 convergences, we can show that the 2 regularity conditions on our definition is satisfied. Okay, step 3 is showing the decays, the 2 decays in the conditions. And this is achieved by the lower semi-continuity of the weak convergence, Fatou's lemma, and since these 2 are non-negative, this is obviously non-negative. This is non-negative since Tk is increasing. So this is non-negative. Therefore, it suffices to show that this limit is 0. And for that, we use the test function 1 over n, Tn of U epsilon on our variational formulation for the approximate problem. We pass to the limit first as epsilon goes to 0 and then as n goes to infinity. And we will get this. So finally, we have step 4, which is to show the renormalized formulation. And we can do this by using Vs of U, Sn is just the plateau function. Then 0 here. So this is 1. And this is negative x. And plus 2, positive. And this is negative xn plus 2. Then 0 outside. This is 2n, negative 2n, this is 2n. Okay. So we use this test function and we pass to the limit first as epsilon goes to 0 and as n approaches infinity. So to pass to the limit, we used Lebesgue-dominated convergence theorem for most of it. And we found some difficulty, although not so difficult as the previous difficulty, for passing to the limit in the interface. So that is our result. So thank you very much for your attention.